In this example, in this video, we're going to take a look at an example of Neville's method. So what is Neville's method precisely? Well, Neville's method, it tells us we can recursively generate a Lagrange polynomial by taking previous Lagrange polynomials. Now we're going to choose very specific Lagrange polynomials, although it works for any type of Lagrange polynomial. But we're going to say we're going to build on the Lagrange polynomial that ends at j and begins at j minus I minus 1. And so we'll have x minus x sub I minus the Lagrange polynomial that ends at I and has that same kind of width, j minus I minus 1. And so we have x minus x sub j as a subscript over x sub j minus x sub I. All right, so the way we're going to build this new polynomial is by doing this. However, we're not just going to build the new polynomial, we're just going to go ahead and build the new approximation. So we won't even see the new polynomial, we'll just see the new approximation we get if we add on another node. And then what happens if we add on another node, and then add on another node. So that's what we're going to do. So again, I'll rewrite that. We're going to have x minus x sub I q j minus I minus 1 minus xj qi j minus I minus 1 all over the difference between xj and xi. So not the difference in the indices, but the difference in the x values themselves. And we will assume that the value j is greater than I, so that we're tacking on an index later on in this process. All right, so here is our example. We have this function f, and our function f has x values of 1, 1.3, 1.6, 1.9, and 2.2, and these associated function values. We are going to use these values to perform Neville's method and construct an estimation for the function value of this thing at 1.5. Now, notice here, we don't even have the function, we just know function values of this thing. And so we're estimating this thing because we just have measurements at specific points. And so what we're going to do is we're going to create this table. The x value here that we are going to be using is x is equal to 1.5. And so when we take these differences, if we take x minus x sub I, so our first point is 1, so 1.5 minus 1 is 0.5. 1.5 minus 3 is 0.2. 1.5 minus 1.6 is 0.1, negative 0.1, then negative 0.4, and negative 0.7. If we use just a single point, then we have no other information, and so that is the best estimate. So that is our Lagrange polynomial when we use just a single node. So now, if we wanted to use 2 nodes, we're going to generate our new Lagrange polynomial. We're going to take these 2 into account, but we're taking them into account in a very, very special way, right? So we are going to take this value, this 0.5, and that 0.5, we are going to multiply that by Q10. And so Q10, we're going to multiply that 0.5 by this value right down here. And then from that, we will subtract 0.2 times this value. Right, so we have 0.5 times the 0.62 business minus 0.2 times the 0.76 business. And what does that get divided by? All right, so this is where we're using Neville's method, right? So this is where we have that 1.5 minus the x sub I for the first x sub I, right? That's why we use 1.5. And then we have from the next row down. But all that's divided by xj minus x sub I. So xj minus x sub I, in this case, our x sub j is 1.3, x sub I is 1.0, and so that difference is 0.3. And when we evaluate that, we are going to get something like 0.523, 3449. And so that is an approximation for this function value at 1.5 when we use this node and the function values that we happen to know there. However, what if we used these two nodes? Well, if we use those two nodes, we can build it in a very, very similar fashion. So we can take our difference between 1.5 and the x value, the node value of 1.3, we will multiply it by this 0.45 business. And maybe I'll write this in a different color. I know I already started writing it in one color, but let me change colors here so we can differentiate this. So we're taking these two. We're taking this point, the 0.2, times the 0.45 business. Minus the negative 0.1 times the 0.62 business. And all of that is going to be over 1.6 minus 1.3, which again is actually still 0.3. Because all of these nodes are equally spaced, that's going to happen. And we like to use equally spaced nodes. It's not a requirement, but it's certainly nice when that happens. And when we do that, we get a value that is approximately 0.510 to 0.5102968. And we can continue this process, right? So if we did this process again, we combine this value and this value. In the same way, we're taking this value here times this value down here minus this value times this value. And then we're dividing it by the difference of those two values. We get something like 0.5132634. And if we did it yet again, we would have something like 0.510 4270. And so those are those values of q sub I, comma 1, right? So we're using two nodes spaced one apart. Now, what if we use three nodes? And so we have nodes that from the first node to the last node, the distance is 2. So we're going to have ultimately 3 nodes. When we do that, we go through really the same process. Now, we have to be careful about it. So it is the same process, But we do need to be careful. So let's say here, we're going to combine this value and this value. How do we combine those values? Well, we take this value times the node that was used in constructing this value but was not used in constructing this value. And so the x minus that node, right? And so what that looks like is we have this 0.5 business times all the way back up here to this specific 0.5. Okay, so we have 0.5 and the 0.51 business minus, then we're going to have this value here times this value down here, right? So when this estimate right here was constructed, it used these nodes to construct this estimate. It did not use this node. And when this estimate was constructed, it used these two nodes. It did not use that node. And so we're going to multiply that next one by negative 0.1 times that 0.52 business. Right, this stuff right here. And all of that is the difference between the two nodes on the extreme. Right? So we went from x1, from x0 up through x2. And so they're different by 0.6 now. And when you make that approximation, you get something like 0.512, 0.5124715. And we can continue this on ad nauseum forever and ever and ever and ever, right? So we would combine those two. And when we combine those two, we'll get something like 0.511 2857. When we combine these two, we get 0.51137361. And then we construct again, right? And so we're going to build our next estimate off of our previous estimates. Right? And so we can combine these two. When we combine those two using the Neville's methodology, we have 0.511827. When we combine those two, we have 0.5118302. And then finally, when we combine all of everything, then we have, and so I'm going to go ahead and write out this calculation again so we think through it. So we're going to have this approximation, the 0.51180302. So we have that value. That value gets multiplied by 0.5, right? So it's getting multiplied by this because this value, what nodes did it make use of, right? So kind of stepping back, it made use of all the way back up here. It did not make use of this one. So we're going to have 0.5 times this value minus, and for the other piece we have this value. What did it make use of? Well, it made use of, so tracing this back, it made use of everything. Oh, hold on. I have to trace it back well. So to there, to there. That green one makes use of this. So it made use of down to the 1.9, but it did not make use of that 2.2. And so we will have negative 0.7 minus a negative 0.7 times the 0.5118,127. And we are going to divide that by the difference between the two nodes that were excluded. So the two nodes on either end. So 2.2 minus 1.0. And when we do that, we get a value that's like 0.5118,200. That's the value right here. What if we wanted to get a better approximation? What if this approximation wasn't good enough? So the way we could do that is we can just tack on another row. And so this is really the major benefit of this, is we can now just tack on another row. We don't have to recreate all the rest of this because those values still make sense. Those are all still going to be the same. We can just construct this one new row, or new row this way, however you want to think about that, and do that. So that's Neville's method. It's kind of complicated, but it will recursively get our estimate. All right, we will talk to you in our next video when we talk about divided differences. We will see you there.